There were new concepts for many of you yesterday, but yeah, so I will take a little more easy today. Anyway, let me recall a couple of things. We said that if a function, two variables, depends just on one variable, where h is a function of one variable, then we said that the wavefront set on f must be it can only contain vertical element like that. So how did I express it? And we proved it from the definition.
It's a harmonic set. So psi is 0 R.
Well, one often uses this. Okay, I should this careless. Since we know that the wavefront set is conic, sometimes we use this sloppy notation, just using just normalized C's. C2 any x and C2 different from 0. Put it that way. And we proved it directly from the definition by showing that any C with
When I was making when I was saying psi 1 equal to 0. X2 is not something. Psi 1 is also 0.
Yeah, it was there before.
Yeah, thank you.
By choosing the cutoff function phi in the definition by as a function of two variables. I mean, as a product of one function of x1 and one of x2, and then observing that in this situation, if the cone we can choose a conic neighborhood of this such that whenever the absolute value of C tends to infinity, while C stays in the cone, then phi hat of C1 has to tend to 0 very fast, and this is bounded. So this argument proves that such wavefronts cannot occur if there is such a function. And also, of course, if H is smooth, there is no wavefront at all. So the wavefront set will consist exactly of such pairs where x2 is a singularity, it's in the singular support of H. And this is, of course, true for several variables. x1 can be several variables, and also we shown that the wavefronts behave as we want when we change variables. So if we take a smooth function of many variables, Vx, with smooth, with gradient different from 0, and pick up fx depending only on the values of phi. Then the wavefront set can only wavefront set of f can only contain elements that are with C vectors perpendicular to the level sets of phi. Contain such. And the reason was that we can, by a smooth changing wave value, we can let's see English words. We can, the situation can be transformed. Thank you. Okay. So then I probably told you that if we should mostly consider real value functions. If f is real value, then the Fourier transform is symmetric under the wavefront set. So C is in the wavefront set if and only if the opposite quantity is in the wavefront set. This is because then the value of the Fourier transform for the opposite side is just the complex conjugate. But there are, I think I cannot speak about this without mentioning the fact that there are cases for complex value there. So really, when I looked over, I think it's better that if you excuse me, I get the minute before I went here, I looked over my talk and I forgot the paper on my desk. So that was the little constants will be wrong if I don't. I'm sorry.
Have you finished? Sometimes we try to find a friend.
So the little constant will easily be wrong if you don't look at it. So the general principle is that boundary values of the holomorphic functions from one side of the real axis will have the properties that we are after. So consider 1 over x plus y for positive y. X minus as this now tends to what I write pi 1 to x minus pi delta 0 as y tends to 0 from the upper side. If it tends to from the low side, the sign here will change. What do I mean by this? Well, sometimes in English literature it's called PD, principal value, but it was invented by French. Perhaps Cauchy even. Definitely used by Harmonic a lot. Valeur principale. This is a distribution defined, as you may know, because the function 1 over x is not locally integral, so that does not automatically define the distribution. But for test functions, this principal value converges. Epsilon tends to 0. And now I claim that the Fourier transform of this distribution is some constant times the Heaviside function minus 2 pi I, where Heaviside H is this jump function C1 for positive C. And why is this? Well, let me tell you. You might like, if you haven't seen it before, the trick to compute the Fourier transform of this principal value. That we can take Fourier transform, but how do you? It's not completely straightforward if you try to do it from the definition. But here is the way. You verify that if you multiply, it becomes 1. This is warn you to verify this. You have to do the definition, use the definition of multiplication of distribution by a smooth function. That is, you have to the action of this on the test function is the same of the action of that on xp. If you do that, you will get this result. And then if you use the formula, remember this, because if you write down the definition of the Fourier transform, you see that the derivative C of f hat is the same as the Fourier transform of minus ix f hat. So we can put the I here. So if I call distribution by U, I get from this that the Fourier transform of x u must be I derivative of the Fourier transform over. One. Now the Fourier transform of the Dirac distribution is 1. So using the inversion formula, you get 2 pi delta c. Now we integrate. Here we get x u hat c must be 2 pi I sine function or pi I. I'll explain in a minute. Plus some unknown constant because of this expression. What do you mean by sine function? That is the function which is plus 1 for positive c and minus 1 for negative. So the jump here is 2. So that's why I got rid of the 2. Now, u, this is an odd function. So its Fourier transform must be odd. Something is wrong. Yeah.
When you write the derivative in the second line, why is it delta?
You have. Wait a minute. What did I do wrong? I use this. X u hat is what did I do?
Right hand side should be the derivative of the Fourier transform of the u.
X u hat must be the derivative of
the Fourier transform of u, not of 1.
Yeah.
Yeah. Derivative of u hat.
It's dc u hat.
Yeah, yes, okay. Yeah, this I just get from here. But now I use the formula. So
it's not the root of the function, but it's just the function. Root or use this function.
So you first compute the...
Yeah, I compute this.
No, but there's no derivative. You see, you have the function.
You mixed up two things in the same form.
Yes.
Maybe you should restart.
Yes. Yes. I want to compute you had, and I know this. Now I take the Fourier transform of both sides. The Fourier transform of that is this, and the Fourier transform of that
is on the formula from the right.
it is I get from here. It is I delta c of u hat.
Exactly.
And now integrate. I get I u hat is equal to pi sine function psi plus cos. Now I know that u is an odd distribution, so u hat must be an odd distribution or function, and can only be the case if c equals 0. So therefore I get this. So now I can compute hat, it should be minus I pi sine function minus minus I what? Yeah, this is fine. So these two cancel for negative c. So we get the Fourier transform is minus I pi 2 minus 2 pi I x. So now it's an exercise that I need to do to verify that. It follows from this that the wavefront set of f can only with the sloppy notation that which is common, that 0, 1 is in the wavefront set. But minus 1 is not. Well, this is correct, actually, it's not sloppy. The other way around. And the reason is that because the Fourier transform is 0 for negative c. So to verify this, we use the definition. We take the pattern function supported near zeros, and use the fact that the F hat is convolution. And we need to verify, which I need to do, that this convolution in the negative direction tends very fast to 0, since phi hat does, because f hat is 0 in that way, but not in the positive direction. So that's it. Another way is to start from the function that's called u epsilon x equal to 0 for negative x and e to the minus epsilon x for positive x. You can compute its Fourier transform. It will become one directed, and it will be 1 over xi plus epsilon or something like that. And letting epsilon tend to 0, you get about the same information. So we have done that. Next, what I was about to do was to discuss integration over submanifolds. Let's say we have f is a characteristic function for a disk in the plane. I just draw it like that. One here. And let's say we integrate T we integrate parallel lines parallel to the x-axis and get a function of just the second variable.
So kx1, right? Kx1.
Is that?
Isn't it right?
No, it's fine.
Right.
Don't see from my end. Kx1.
Oh, yeah. Yes. Okay. Okay. I should be careful with it. So we can actually compute the result will be something like 2 squared 1 minus 2 squared, something like that. So the function is smooth, except at these points where the line which we integrate over meets the boundary. And that has to do with the wavefront set. We learned that the wavefront set of this function f consists only and precisely of the conormals of the boundary of the disk. And this is what creates the singularity in the result here. So more generally, the idea is, the fact is that if, I think I wanted to assume see how I wanted to write it. I want to assume that there are no simply that all wavefronts like that are not allowed to be in the wavefront set. X well, it's you have always a choice. 2, 0, C2, not in the wavefront set. Nothing of this sort is allowed. And we assume f is compactly supported. But it can be a distribution. Then Ex is COT. The reason is pretty simple. We know by definition that if we cut off phi with cut-off functions f and take Fourier transform, it will decay rapidly. See in cone, double cone, like that. And in particular, phi f hat 0 C2 is less than indicate rapidly like that. We're only asking. But this function is Fourier transform of not precisely G, but almost. It's the Fourier transform of H2 C2 is directly from the definition of the Fourier transform, but it's also a special case what I heard Hayek told me about the Fourier slice theorem for the Radon transform. So, therefore, this function is simply. We know that in Fourier transform decays fast. And then we do just partitionally. So we chop up F and G as a sum of finite number of functions that are C infinity by this. And the example is a special case of this. Now, it's fun to observe that this argument proves slightly more general, that if we have a slightly weaker hypothesis, namely, what is the hypothesis? That this here I meant, of course, for all real. But we only assume for positive C, they are absent. Let me emphasize this by this sloppy notation. Then the corresponding not at the integration pop up in G. The same argument proves this if you look at it. So this has a useful consequence. You remember yesterday I mentioned one of the enjoyable examples you might entertain yourself with to apply the definition. It could be any such a corner region, could be any corner. The function in the plane is one here. I never checked what happens at the corner. You might expect that, for instance, just those or something like that come up. But actually, all projections above that point will be in the wavefront set. And this follows now. Why? Namely, we can integrate over a family of parallel lines, form a function depending on t, say, or t, by integrating f over x dot omega equal to t. That's like a Radon transform. Then we know, and we also see directly, that there can only be singularity in P at this point because there are definitely no wavefronts in the F that are orthogonal to the lines of integration, except possibly here. But if we compute, we can compute G. The values of G will be just the length of that segment. So GP will look like that, the graph, because it will be 0 here, and so it follows directly from the definition that both at that point, both directions are in the wavefront set of G. So in particular, particular, it follows from this that in particular those must both be in the wavefront set of F. Is that clear? Oh, it was a little abstract yesterday. I thought I'd go through some examples very clearly today. So now, varying the direction of the family of lines of integration, we conclude that, say this is A0, hence X now C is in wavefront set of F, or all C different from C. Yeah. Everything is clear? Okay. Then I'm going to move to slightly harder stuff, but not so. What did I do? I'm going to consider now the plane Radon transform. In geometric notation, the F is a function of the plane. Or Fn is just the integral, so F has convex support over the line. Here is the support of F, and here's the line, with respect to arc length measure. So we are interested now in singularities. So if we know something about the singularities of F, can we say anything about, in general terms, about the singularities of this function? This is a function on the manifold of lines. It can be smooth or not. So we can say very little if we don't adopt the language of wavefront set, because what is obvious is as long as L doesn't meet any singularity of F, the Radon transform will be smooth off. But say that F has a singularity here, then this may give rise to a singularity in RF, possibly on any line meeting that point. So it can pop up anywhere. And conversely, if we know that this function has a singularity on a specific line L0 as a function of F, the origin of that could be a singularity of F at some x0 on any point on that line. So we can say very little. Therefore, it may appear surprising that if we describe singularities in terms of wavefront sets, there is a 1-1 correspondence between the singularities of F and the singularities of RF. And that's what I will describe. And this, again, is a special case of many more general things. So even if you are not going to specialize in Radon transforms, it may be useful to understand the way of thinking and the terminology used. So now the first difficulty we have to handle is how to describe the cotangent vectors about on points on that manifold. So we need coordinates of this. So I'm going to, since the problem is completely low, not completely, but almost low, I'm going to use coordinates that are suitable in a local situation. Namely, I will parameterize the lines as follows. So the line parameterized by y1, y2 as slope y1 and its position is determined by y2. So RFY is integral. I just plug in the values of x2 from here. That's y2. dx1. Now, there's a slight difference. This is not the arc-length measure, but if I choose the arc-length method, here it would just be a factor depending on y1, square root of y something. It wouldn't have any effect on the problem square study. So this is my transform now. So the good news is that the source of information of the relationship between the singularities of F and RF is in the wavefront set of the Schwartz kernel of this operator. So the first thing we will do is to write down the Schwartz kernel. What is a Schwartz kernel? Well, it's KFY
FX.
X. X and Y are not. We want to find this here. That is easy. It will be a measure on a hypersurface in the four-dimensional product space. Namely, I can write this as in the integrand. I can write as an integral with respect to x2 of the following thing. Well, yeah, x1, y1 plus y2, delta 0, x2 minus this expression. So this is the integral. Why? Because
You want x2 and
probably something wrong.
no, in the x2, you want x2 with the f.
No, yes. 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 Yeah, this is what I wanted to rewrite. I copied it. So I just use the fact that phi x2 delta x2 minus a x2 is equal to phi a. So therefore this comes in here. So this is the same thing. So this means that the first kernel kxy is this thing. So, what is the wavefront set? This is a function of four variables. What is the wavefront set? Well, it's In the first couple of minutes of today's talk, I gave you an example. I mentioned something of which this is a special case, namely, I wrote something like some wavefront set or something like that. And this is a special case now where phi x to this 4 variables and h is as a data function. So in our case now, phi xy is this state. x2 minus y1, x1 minus y2. So what is the gradient? Well, let me write it this way. Gradient is y of psi. With respect to x1, we get minus y1, 1, and with respect to y, we get minus x1, minus y. So actually, the outer function h is a delta function. It has a singularity where this is 0. So there will definitely at every such point there will be wavefronts in the direction of this gradient. So wavefront set of k consists, it's now 8 variables. 4 plus 4 variables. It is precisely equal to xy c eta, where phi xy equals 0, and let me c eta is a multiple of that. Namely, c equal to lambda minus y1, 1 eta equal to the same lambda times minus or x1, 1. So, now I can actually state this theorem. The wavefront set of RF is equal to the wavefront set of K prime. I will explain that. Composed with wavefront set of F. What does this mean? Well, prime, first of all, means that you have to, for reasons that will be clear, that you have to change the sign of the eta vector. Let me do this here. In order to say it rightly. So by definition, it's the same object with the minus sign in front of the eta. So I can also change here. It will be clear why this occurs in a moment. And what is this circle here? Well, it's actually in the special case here, we shall verify in a couple of minutes that, well, let me put this. One observation first. We shall view this as instead as a set of pairs. This is at present, by definition, it is a subset of T star X cross Y, which is the cotangent manifold above this product space. But there is a natural isomorphism. So we can always, if we prefer, which we do, to view this as a subset of the product space like that, which means concretely that we want to do this as a set of XC pairs of pairs. And then comes the same specifications as before, of course, etc. And CNN. Why is this? Well, it's very simple. The elements of a cotangent space are, by definition, linear forms of the tangent space. So, if you have a linear form of the product space, it's in a completely trivial way, it's a product of the linear forms of the two spaces. It is just if say C comma eta acts on U comma V, it acts as U acting on C plus V acting on eta. And there we are, the elements here. So it's a trivial fact. So now we have actually a set of pairs of elements, which themselves are pairs. And now I'm going to tell you, we are going to see in a couple of minutes, or perhaps tomorrow, since I was slow in the beginning, that this set of pairs is actually one-to-one, so it's a function. I was taught long ago that a function is actually a set of pairs with a certain property. It's a Bourbakistic way of talking about functions. So now we are going the other way. We start with a set of pairs, and we learn that it is one-one. So then, in that case, this circle is really trivial. It's just this function maps on that. Since it's one-one, it takes this. This is a subset. So here we have the subset, and here is the other. And here is this one-to-one, and so this subset, whatever it is, will bring us a subset here. But in the more general case, that it's not one-to-one, it may contain thick pieces like that, then one element here will produce a whole bunch of elements there. So it's a very simple operation. So this is the theorem. And I plan to prove to you this inclusion today, but I won't have. We can do it from the definition. And then by the inversion formula for the Radon transform, we get very easily the other. So what I can do still is to verify that it's one-to-one. So, where is it? I don't want to write slow. So let's say given x0, c0, I want to verify that this introduces one specific. That there is only one y eta coupled to this one. Why is this? No. Now, first of all, we have this relationship. So our y must satisfy y x2 equal to y1 x1 plus y2, and now yes. So the y's must satisfy this, and moreover, c is given. So but we can wavefront sets of conics, so we can normalize C, so that C0, so that lambda is 1. So we get, clearly we get y1. Y1 is equal to minus C0, 1. Epsilon. So then y2 can be computed from here. Remains eta. It is here. We know lambda is 1, so we get eta 1 equal to, we get eta 0. So y2 from here, and then eta 0 is x1. So we can do this the other way around. So we have shown that it is 1, 1. Now, I plan to, when, if I have, we learn a huge amount if we can express this geometrically, what we just did. So it would be good if I could do this. Given a line, you're given a point and a cotangent vector. We saw that this relationship specified a y that is a line and a cotangent vector above that line. We want to just interpret what we just did geometrically. What I claim that the line that was given to us by that y we computed is the one that is perpendicular to C0. Yes, of course, because the line in y has the equation x2 y1 x1 plus y2. So it's normal is this is the law of the line, of course. So that's geometrical, that would, and now more interesting, just as easy, but maybe not quite as trivial how to think. I want to show you the geometric meaning of the eta. I claim that if we must, what is fun with this, the area of Radon transform, is that they're always going back and forth between geometric thinking and algebraic thinking. So we must think of the set of lines through the given points. y space in these coordinates. Geometrically, it's a family of lines rotating through it. But in those coordinates, it's a line which is given by this equation, just that now y1 and y2 are the variables. And now, what is the y2 equal to minus x1, 0, y1 plus x2, 0. What is the normal of this line in this plane? I don't know where I write it anyway. It is a plus minus x1, 0, 1. Yes. Isn't it? And this should be our A bar. Yes, that's what it is. So geometrically, now we have freed ourselves completely from those coordinates. The given a point and a cotangent vector, the corresponding element under that corresponding in the cotangent space of lines is a pair, the following pair. The line through that point, perpendicular to that cotangent vector C, and the cotangent vector in y line space above that line is the cotangent vector, the conormal to the set of lines consisting of lines rotating through that point. I will comment on that last thing. I will repeat it in a more general way and comment it.
Right, so I didn't quite understand that. So what is the cotangent vector in the space of line? How do you think of it?
Yeah, yeah. Thank you for this question. That's what I plan to come back to. Well, in general, if let's think of an arbitrary manifold and a point on a manifold. What, in this case, y0? What is a cotangent vector? Well, I recommend, as soon as there is need for it, to think of the cotangent vector not as a vector, but instead as its zero. The cotangent vector is a linear form on the tangent space. So, but since we are disregarding the magnitude, and in most cases we can also disregard the sign, so it is completely specified by its zero set, which is a hyperplane in the tangent space. So we can think instead, whenever we prefer, of a hyperplane in the tangent space. Now, on a vector space, a hyperplane in the tangent space is conveniently defined by a hyperplane in the space. But now, on a manifold, we don't have hyperplanes, but we have hypersurfaces. So any hypersurface, any two hypersurfaces which are tangent at the point, they specify the same hyperplane in the tangent space at that point. So they actually give us, by the way I said, a cotangent vector up to multiplication by step. So that's what we did here.
But then here the manifold is of lines.
Yes.
So what do you mean by a hypersurface in the space of lines?
Thank you for the question. That's what I was going to say, but I'll run out of time. If we have, I can repeat it tomorrow, but we have instead hyperplanes. Then if you fix a point we are considering the manifold of hyperplanes in Rn instead of fix a point in Rn and consider a little piece of a hypersurface in the manifold, namely the allow fix a hyperplane first through that, and then wiggle it a little.
Correct.
That defines a piece of a hypersurface in the manifold.
So, but you can't wiggle it in all directions because then you get the full open neighborhood of a point.
That's right, but you have to wiggle. By wiggle, I mean keeping it through the point.
I see. So
that has the right dimension.
I see.
Because it's just one condition.
Correct. Okay.
So it's a hypersurface. But we'll go through that tomorrow.
Okay.
And that specifies the cotangent vector.